Hi guys. So we had a look at what is control theory and how we can use open loop control to create simple controllers. Let's now look at closed loop control design. What is closed loop control? Well, exactly like in open loop control, we have an output signal Ys and a reference input Rs. Here though, we take the difference between the reference input and the Ys output in order to measure the error between the two. This error is written Es. It is fed into a controller, which is an algorithm that computes a control signal Us in order to minimize the error. This control signal Us is then fed into a plant GPS in that case, which produces an output again, itself fed back to the error, and so on and so on. This is why it's called closed loop control, because there is a whole feedback system between the output and the reference. Closed loop control has many advantages. First of all, it is not necessary to know the plant perfectly, simply because the controller can adapt to different plants. So you do not have to know the transfer function of the plant perfectly. Secondly, it is able to adapt to significant disturbances. Once a big disturbance hits the system, the controller is able to take it into account and then output a control signal that will correct the final output of the system. Thirdly, the poles of the plant can be arbitrary. Unlike in open loop control, the plant does not have to be stable. A controller can actually take an unstable plant and make it become stable. Finally, in this case, control can be very precise. You can reach your desired output value very accurately in impressively short amount of time. As we briefly explained on the first slide of this lecture, the control target is usually to bring the error ET as close to zero as possible. So in this case, with ET equals RT minus YT, we want RT as close to YT as possible. Closed-loop control systems are based on feedback. The control error is part of the system and actively being minimized. Let's now look at a real-life application of closed-loop control. More specifically, we are going to look at the closed-loop speed control of an electrical motor. So here, we have a resistor RA in series with an electrical motor to which a voltage Vi is applied. This electrical motor is connected to a rotor which has a mass of inertia J at its end and a damper of damping coefficient CR. Obviously, the motor, to rotate this whole rotor, has to apply a torque TL to the system. So first of all, we have to build a plant for that. The plant is made of first the driving circuit dynamics, which are essentially this electrical circuit, including the motor. We then have to take into account the torque necessary to rotate the rotor, so the torque applied by the motor on the whole system. We then compute the rotor dynamics to check and anticipate the final angular velocity. We then use sensors to measure that velocity and also take into account the dynamics of these sensors, so the slight corrections that need to be applied to it. The final value is our output Yt. This output Yt is fed to the error between your reference velocity that you want to reach. So you have a reference velocity minus that output Yt, and this builds the error. The error is then fed into our controller GCS, which outputs a control signal, in that case the voltage Vi. And this is an example in the form of block diagrams of a complete closed-loop speed control of an electrical motor. So what is the difference between closed-loop control and open-loop control exactly? Let's look at very practical real-life examples. Imagine a person picking up an object. in the case of open loop control, that person would actually be blindfolded with no idea of what it is picking up or where it's going. In the case of a closed loop system, that person would have her full sight. It would know exactly where it is going and what it is supposed to pick up, and it would do the job fast and accurately. Let's look at a home heater. Open loop control would be a gas fireplace, which just burns fuel with no idea of how hot the room is getting and how long it had to ask for to reach the desired temperature. It just burns and we see what happens. In the case of a closed loop control system, we have a central gas heater with thermostat. So the central heater is actually using the thermostat to kind of tune its burning rate and adapt to the current temperature of the room. We finally reach the temperature that is desired in the target room. Finally, let's look at a pop-up toaster. An open-loop pop-up toaster is a pop-up toaster with no sensors. It just pops after a certain amount of time. In the case of a closed-loop control system for the pop-up toaster, it actually has humidity and heat sensors to know exactly when to stop and pop up. When designing a closed-loop control system, there are several performance criteria we are trying to optimize for. First of all, the closed-loop stability of the system. We want our system to be stable. We want its oscillations to die out progressively. Secondly, we are looking for the transient performance of our system. The transient performance is how the response of the system performs before it becomes steady and settles down to a constant value or a constant behavior if there are still oscillations. So this kind of transient performance criteria are, for example, the rise time, which is the time it takes to reach about 67% of the peak of the overshoot. We have the overshoot of the response, so how much does it go over our desired output. We also have the settling time, so how much does the response take to settle and reach a steady state. The position of the poles of the transfer function of the system in the left plane actually influence the damping and settling time of the control system. So essentially, the position of the poles in the left plane, for example, how left are they or how right are they in the left plane, will have a direct impact on the oscillations of the control system as well as the time the system takes to settle down to a steady state. Let's now look at the closed loop steady state performance with and without external disturbances of systems. So first of all, how do we calculate the steady state performance of a system? Well, we look at the error and take the limit of that error with respect to time, so we're back to the time domain, when t goes to infinity. Okay, and we know that the error is actually equal to r minus yt. We also know that we want that error to be 0 in the long term. So we want the steady state error to be 0, always by definition. In that case, it also means that we want that the limit of yt, so the output of the system with respect to time, is equal to r, our reference, or a constant with respect to time. And this is as time goes to infinity. And we want that even if r is different from 0 and even if there are disturbances in the system, d being disturbances here. The graph below actually shows good closed loop control and poor closed loop control. So here, like before, we have a plot of the angular velocity of a motor turning. We can see that at some point we want the motor to ramp up its velocity. That's where the demand R changes. Good control and poor control both react, however poor control stays away from the reference that we desire, while good control catches up to that reference quite quickly after the step input. At some point though, there is also a disturbance that takes effect. As we said earlier, a disturbance can be a gust of wind, it can be someone else, getting in the car, adding 100 kilograms of weight to the expected weight of the car, stuff like this. So here, suddenly, in the case of good control, there is a slight dip in performance with the control actually being a bit lower than the demand reference, but the controller acts and actually sets back the output to the desired reference. However, in the case of poor control, the disturbance completely disturbs the system. It goes even further away from the demand reference and stays away without efficient correction to the problem. So this concludes our lecture on closed loop control. We saw how much more complicated it is than open loop control to implement, but also how much better it is at actually doing what we want it to do. As usual, if you have any questions, please do not hesitate to ask me, guys. I'll be very happy to help you. Thank you.